Doing it finally with a projectile motion item. So we're doing a sphere, basically a sphere. We're doing a Reynolds number first. So the bottom is Reynolds number, and the top and the side is the coefficient of drag. Only way I know how to solve this question. So we're doing a sphere, like I don't know, a very smooth sphere because we're not doing a rough one. We could do a rough one, and isn't that different from what I'm doing with the smooth? So the first thing we do is get the area. Got the area. And then we get the length we show over here. And then I don't think the bounds are correct. So I use a little bit iffy because I just kind of approximate by visual effect. Um, so. It is a little off over here. It kind of goes off over here and I jump like this, which is fine. It's not that bad. You can mess with the bounds a little bit. It's not gonna be accurate. Whatever. So next thing I do is I change the coordinate system because I was a fool and forgot to change it properly. So I was supposed to do minus on mg and plus on the drag. But because I messed up and then plus an mg and minus on the drag because I always thought, hey, it's reverse drag. So you're gonna have to assume that the motion going down because it's always resisting motion anyway, so it's actually perfect. It makes more sense for it to be negative. So mg is going to the direction of the motion in this case. So we're doing mg like this. Um, Bonkers. So my bad. My bad on that one. But it shouldn't matter too much. The coordinate system changed. It's fine. Even though I fucked up. Basically, I fucked up. Okay. It still gets the same answer, so we're fine. But you're gonna have to assume that this going downward is positive in this case, which is just natural, I guess, for me. It's the path of motion. It makes more sense. Kind of doesn't. Um, ew. So in this case, um. mg is positive, and then as you can see, the motion of this thing is negative. So we're going for velocity for now. I could go for easily the this for the next section, which is gonna be just first, you know, but I'm too lazy to do that. So we start off with Reynolds number and the coefficient, and then we get this too. And now notice that there's like a linear line over here and then a flat line. So we go over here and say, okay, linear line and flat line. So we have two different differential equations. The first equation turns into a linear relationship, which is quite cool. So it's like and then the other one is a little harder. So as you can see, annotation. I wish there was a red dot animation for this one, but as you can see, this is a linear approximation and this is a cubic approximation. Um, this is actually more accurate for the bound region if you exclude that. The bounds are a little bit, well, I think it's a 3 instead, honestly. I need to double check that. So what I'm trying to say basically is that this bound is more correct because it approximates well as a flat line approximate well. While this one is like this, but the gra as you see the graph, it goes like this. Like so it has a large error near over here region. So I would approximate I mean if we had the bandwidth and the power, you could use this approximation to make it better. The problem with this approximation is that it introduced another V and another V over here. So when you cancel a V out, you actually don't cancel the whole thing. You have a V square, which is another cube root over here. But it's not cube root. Actually, it's a 0.8 and a 6. So you're gonna have to do math on more differential calculus on this. And I never taught you yet how to solve for any of that, which is going to be numerical analysis. Honestly, I will not solve it analytically. But I mean, probably could actually, with a little bit of a headache, but you probably could. Um, but this is kind of what I went with. No, not that one. No, that one's a pretty good approximation. This approximation is kind of what I went with. Notice how this approximation can account for V0 being literally zero velocity. Because Reynolds number has zero in here. I mean, it's a little greater than zero, but we can kind of see over here, this one, this linear approximation over here, can account for zero. While this one, because it doesn't have a bound of zero, you can't have an initial velocity of zero. You need to figure out the Reynolds number equivalent in there. You have to do all the math on that, or you can just see, you can figure out the math to get the limit velocity to figure out this accurate time scale. Um, Either way, you can kind of get what I'm trying to say. But I'm also assuming an infinitely long, um, uh, infinitely long cliff, and yes, an infinite left cliff. So. You also need to test out if the velocity is gonna reach terminal velocity here, where it won't increase anymore. Um, so that's interesting. Yeah, so there's also gonna be cases where it might reach terminal velocity, uh, which you should be able to check very simply. Um, yeah. Also, the second order one has terminal velocity of 0.3. I mean, it depends on the actual K and everything. So the second method, I actually kind of know how to get the terminal velocity easily. So this one, I know how to get the terminal velocity easily. This one, I am not so quite sure. I think the E to the thing is too small to create a terminal velocity. Um, is there a terminal velocity for that? I don't know. Hmm. Isn't um uh, we'll figure that out later. So for now, we're gonna go on here and continue. So we do all the math here, and we see we get this and this, and actually we can really quickly get the second one. You can get the x position by just integrating this. Really quickly. And over here, you can see, okay, let's integrate over here. That's going to be in the bottom. So you're just going to have to 1 C divided by K1, and that's just going to be a negative, right? Oh, that's going to be a negative, and this is going to just have uh, T over here. And make sure that's let me check the root of that. It's negative. Right? Yeah, that's true. I always get those confused, and you can just add a C1 here. I believe the integral of this is, if I remember correctly, I think it's ln cosine h. Just going off from memory now. Cosine h plus c underscore 1. Remember correctly, the integral of that is that, and I think, if I remember correctly, that this has, if my memory state serves correct, this should be your next x. Yeah, that should be it. Hopefully I'm correct. If I'm wrong, I'm wrong. But I'm pretty sure that's the integral. So linear drag, let's see if it can have, uh, yes, it has a terminal velocity. Uh, So I guess that means that theoretically, um, if you're in this region, you have a different terminal velocity as this region, depending on the RE calculations over here. Interesting. I did not realize that. So terminal velocity is when the dT/dV equals zero. And then what happens is that when the dT/dV equals zero, you have no bounded forces, and you have because air resistance is a reactive force when it reaches terminal velocity. Okay. Uh, Oh, okay. After solving, you need to check for terminal velocity, I guess, because you can't increase the velocity more if it's terminal velocity. Also, that would sound right. Yeah, that is sound logic there. Um, yeah, yeah. So I think I got it. Uh, so yeah. Uh, because you can't have air resistance pulling an object up. That's physically impossible. So you're gonna have to figure out term velocity. Okay. So let me see term velocity real quick. Uh, note. Okay, I'm gonna write here. Note when uh, okay, dv dt equals zero equals zero. There is uh no then it is terminal velocity. I forgot about terminal velocity. Terminal velocity. This plays a role here. It basically says no, it's like friction. You can't have more than terminal velocity. And I don't like how that was formatted. So I'm just gonna change that and just make it better. Don't worry, I'll be back in a bit. Basically, I'm just gonna write insert new equation uh dB dt equals zero. When this equals zero, then it reaches terminal velocity. Therefore, it no longer has any play. Um, uh, uh, does anyone know what, I don't think they know what happens with this terminal velocity. So I'm gonna have to explain that a little bit. Um, I can move this down over here because we just can. Uh, when there's terminal velocity, uh, it, so the drag cannot be greater than gravity in this case. It can be thrust, so then other force because reactionary 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 force. As you know, with friction, this is a reactionary force, which means that you can't have it do something like magic. You have to have confound reasoning. Uh, but not that's a weird word. I just mean that you have to have another force that reasons out why that force exists. That's basically it. Why did I have to make it so complicated? So I hate it when I do that. It just means I'm bad at explaining. So. Here we have here, we're good. So basically what I'm saying is that when dv dt equals 0, there is terminal velocity. Uh, the drag cannot be greater than the force because reactionary force is yes. I don't know if that's true. Uh, that's just I forgot what terminal velocity, so I'm thinking about it. No, no, yeah. So in both cases, there needs to be a terminal velocity. So this has terminal velocity, this has terminal velocity because this is, I don't know why this is so hard for me. This should be very simple. This over here and this over here. This should be a joke of a, this should be clicking my head right now, but for some reason I didn't think of terminal velocity. Which means all my equations are not wrong. They just need a step function. When the terminal velocity hits, you just have to delete it. Um, which I don't really have. I know when terminal velocity hits. It's when K1 equals to V1. So that needs to be something. Anyway, I'm gonna stop my video. I'm done.